So let's look at the refractive index of a liquid using a concave mirror. Okay, in this experiment we are interested in two things. We are interested in finding the refractive index of water using the concave mirror. Also, we are interested in establishing the relationship between force and then the bending of materials. We'll look at that. Okay, so we have some of the apparatus here. Okay, let's go straight to the setup. So for the setup, this is our stand. We are using the pin. Okay, so this is our pin, and then this is our concave mirror. Okay, first of all, we need to find CP. So when we check the table we have here, we'll do one for air, we'll do the other C prime A for water, and then this one for glycerin. Okay, so first of all, for the one with the air, what we do is that we have to keep adjusting this. We adjust this till a point where we can find the pin in the concave mirror. Okay, we are interested in finding the pin in this concave mirror. Now, what are we expecting to see? We are expecting to see a pin that is inverted. Realize that the pin is like this, but in the mirror it will appear like this. Okay, in the mirror. So that's one function of the concave mirror. It gives inverted images. Okay, so the next one is that for the pin that is inverted, the image of the pin in the mirror, it needs to be the same size as the object. So we keep adjusting this to a position where we think the pin in the mirror is the same size as this object pin. Okay, so that's these two properties. We are using these two properties. One, it should be inverted, which is obvious. And then the second one is that it should have the same size as the pin, the image we are seeing, or the object. Okay, what we see here physically should be the same size as the one that we see there. Okay, so when we check well, we should be able to see the pin in the mirror. Okay, so after you see the pin image in the concave mirror, right, that position where you think is the same size and is inverted in the mirror, the image, you measure that position. You measure that position. You measure the position. So you take your rule like this, right? You take your rule like this. You measure. You put it in the center of curvature of the mirror. Then you measure from this point to the center of the mirror. Okay, so we'll record that one here. As our first value for the one in air. We repeat it again. Okay, so it means we need to start again. We start this again from the bottom, and then we repeat it for the second time. And then the point where we find the image again, which is the same size as the object in the mirror, we call that one to be the second value. Okay, then we repeat it for the third time. So we'll be doing it for 3 times. Once we are done with the one in the air, so you realize that this is just the concave mirror, right? This is just the concave mirror. Okay, we didn't add anything else. So once you are done with that one, then we take water. Okay, so this is our water. We pour our water here on the mirror like this. Okay, make sure it fills the mirror up like this. So you can see that I've poured water on the mirror. Okay, then we start again. Realize that the bending of this pin in the mirror when it's in the air or without any water will be different from when there is water on the surface of the mirror. So when you do that, you start again, right? You start again, the same procedure, okay? You start from the bottom, you keep searching till you find the image of the pin, the object pin, which is inverted and the same size. And then at that point, you measure that point, right? You measure that point like this. So you use it again from the center of this to where the pin is. Okay, from the center to where the pin is as your first value. So record that one here. Okay, first value, record that one here. We repeat that procedure for the second time, then record it here. Repeat it for the third time and record it here. Okay, and then when we are done, we can pour this water, right? We can pour this water away. Then we clean the surface of the mirror. Okay, so we can clean the mirror, the concave mirror. Place it back, and then pour our glycerin. So we are done with air, we are done with water, now we are on glycerin. So we pour glycerin also onto the surface of the mirror. Then we repeat the same procedure again. So that's how we fill this table. That's how this is done. Now after that, we need to find the refractive index. We need to find the refractive index of the water. Okay. So what we do is I realize that this particular formula or this particular quantity is for air. This is for water and glycerin. Okay. So we'll come back here and then use with this relation. Okay. Now this is Snell's law over here. This is Snell's law. Okay. Now if we check this, realize that we have two angles here, right? We have this angle and then this angle. Okay. And then realize that this is for the C and then this is for where we find the image. Okay. So one is for C, the air, one is for where we find the image at. You get it? Now this applies to all the three liquids. Okay. So this angle here, which we call I, is the same as this I here. So this angle is equal to this angle. Okay, this is equal to this. And then this angle is also supposed to be equal to this angle. Okay, so this is equal to this is equal to this. Okay, now in doing that, in relating this, we can have this, the sign of angle C, right? So we are trying to express the Snell's law. The sign of the angle I should be the one on the C. The one for the R, the refraction or the refracted ray, is for the one for the C, and then this one is for the C prime. Now in doing this, we get an equation like this, and then from here we get this. If you checked Snell's law, the other videos, you realize how this is done. If this is dividing this and this is dividing this, at the end of the day we'll have a relation like this: QA, QC times QA, QC. So this is C prime. Okay, now this is dividing this, so when it's multiplying, this will come on top, so the relation will change to become QA is dividing here, so it will come and multiply QC prime times QC on QA. So this cancels out this, and then we get this relation here. So that's how they got this. So you realize that it will be left with this and this, QC on QA, QC prime, to be left with QC on QC prime. Okay, now this is the method, and then that's how it's done. Now when you finish, for this particular experiment, you are not plotting any graph, you are finding refractive index. Okay, So we can add, or you see, we repeated it for 3 times. Okay, we repeated these values for 3 consecutive times. So we can add this and then find the average, and then we add, and then we do the same for here and this and the same for here. Now using this relation, right, using the relation, we can find the refractive index of water. Okay, it says that the refractive index of the water should be the QC prime, right, on the QC. Okay, QC. So QC on QC prime. Okay, so we can just take this, the one in air, and then we divide by this. Okay, then we can get our refractive index. Now for the relationship between force and then the bending of materials, first of all, there's no relationship between refractive index and then force. There's no relation between this, but there's a relation between between force and then bending of materials, which is K change in L, right? So this is the deformation. Okay, this is force, and then this is the constant. Okay, so this is a relation. So if you check the other videos, we Hooke's law experiment, you see this is the relationship between force and then the bending of materials. Now the more the force, the more the bending of that particular material. Okay, the more the force, the more the bending of that particular material. So that is how this is performed. So there is no relation between force and the refractive index, but there's a relation between force and then the bending of materials, depending on the type of materials that you are using, whether it's elastic material or inelastic, or it depends the relation. Some of them, when you exert too much force, it will break. Okay, so that's a little for this experiment.